Welcome to lesson 13.4, compounding interest, and this is a growth application. So there's two words there that I want to quickly go over. The first word's compounding. Up to this point, we've been talking about growth applications where they grow annually. So we're given the rate annually. So that's one time a year. Compounding, and we're going to talk about banks here and money, is when they actually pay you that interest not at the end of the year, but perhaps each month. So each month, so rather than one time at the end of the year, they're going to pay you 12 times during the year. Or, and we call this compounding, they may pay you daily. In that case, they're going to pay you 365 times in 1 year rather than once a year. Why is this important, this compounding? Because the sooner you get your money, that interest, the more money you're going to make. And of course, that's what everyone's goal is to make more money. So we want to get this compounding interest rather than just getting it at the end of the year. All right, another important topic is interest. Okay, so interest is when you loan the bank your money. So let's say this is you over here. You loan the bank your money, and to thank you for your business, so they're going to hold on to your money here, they're going to pay you 1%. They're going to give that to you. Now, how do they make their money, a bank? Well, this person over here says, hey, I need a loan from the bank. I want to buy a car. And so the bank says, sure, we will loan you some money. But we're going to charge you 6% interest. So you can see the difference here between them, the bank paying out 1% and them receiving 6%. There's a difference there, and yes, that's how a bank makes their money. All right, two kinds of interest. One is simple interest. Simple interest is interest paid only on the initial investment. And this kind of interest is linear growth. So let's say we're going to use an example of $100 and you're paid 10% simple interest. So the first year, at the end of the first year, you have $100 and the bank pays you 10% of that, which is $10, right? So now you have $110. The second year, you have $110, but they're still only going to give you 10% of the original amount. So they're just basically adding $10 each year to your account. Now, the difference with compounding interest is if you are, your interest is paid not only on the initial $100, but on the actual amount that's in the account. So let's take a look at this. So if we have year one, you have $100, and at the end of that year, the bank pays you $10. Well, now you have $110. 10% of 110 is $11. So then we add that 11 and we have $121. 10% of 121 is $12.10. Well, you can see by this compounding interest that you're actually earning more money and going to earn it faster than the simple interest. Here's a graph of, at first, they kind of start out, you're like, well, that's not really that much difference. Maybe it's a couple pennies, maybe it's a quarter, but over time, it makes a big difference, compounding interest versus simple interest. All right, if you'll pull out your sheet of notes from Module 13 on exponential functions, on the back side at the bottom, you'll see the equation for compounding interest. So we're going to change the growth formula here for compounding interest. And the way we do that, all right, the y over here, or it could be any number. I mean, it could be an a, any letter over here. But this output, okay, is going to be like the final amount or the current amount. Probably more use it as the final amount. This P here is still the initial amount, so the initial amount of money that you put in the bank. Now here's where the growth formula changes a little bit. We have 1 plus, now that part's the same, but now we're going to take R, okay, which is our interest rate expressed as a decimal, and we're going to divide it by what we call N. And in this case, N is the number of times compounded each year. Now I'll come back to that in just a minute. We have our parentheses raised to the n times t. So you see we have n in two places now. Okay, so what is n? N's the number of times compounded each year. So if it's compounded annually, that means one time. Okay, semi-annually means twice, means you're going to get paid every 6 months. You're going to get paid twice in the year. Monthly, let's actually go quarterly. Quarterly means 4 times a year. Monthly would be 12 times a year. And of course, if it was daily, it'd be 365 days or 365. So in the problem, you're going to have to be told how is it compounded, and you would choose the correct number to substitute in for n. Okay, so let's do an example to show you how this works. The Fresh Green Company has a savings plan for its employees. If an employee makes an initial contribution of $1,000, the company pays 8% interest compounded quarterly. So there is the phrase that's important that tells us we're going to use our compound interest formula, which I have written here. Y equals P, parenthesis 1 plus R over N, parenthesis raised to the N T power. If an employee participating in the plan withdraws the balance, so that just means at the end, maybe the person's retiring and they want to take their money out of the plan, how much is there now after all this time? So we want to know how much is in there after 5 years. Okay, so how much is in there? So we're going to use our formula, and we're going to substitute in Y equals, okay, P is the starting amount, so that'd be 1,000, parenthesis, 1 plus, okay, our rate is 8%, so we're going to change that to a decimal, 0.08, divide it by, now the fact that it said quarterly, quarters, think about how many quarters there's in a dollar, there are 4. So our n is going to be 4, parentheses, raised to the 4 times, and we're going to go for 5 years, 5. Okay, at this point you're probably going to need a calculator and substitute or put this in the calculator. Now when you put this in the calculator, I would highly recommend this exponent up here, 4 times 5. I'd highly recommend you go ahead and multiply that in your brain. 4 times 5 is 20, and put that exponent as 20. It's easy to get that 4 and the 5 in the calculator, accidentally bring it down so it's not an exponent. So just go ahead and multiply that in your brain. So put it in the calculator as raised to the 20th power, and let's see how much money. In the account after 5 years, we have $1,485.95. Not bad, seeing how they didn't do anything but put $1,000 into the company savings plan and didn't touch it for 5 years. And look, they made $485.95 as interest. Not bad. Well, let's see what happens if the employee stays there longer and they stay for 35 years. So we're going to have the same equation. 1 plus our interest rate's going to stay the same. It's still compounded quarterly, only this time, rather than multiplying by 5 years, we're going to multiply by 35. Go ahead and put that in your calculator. And we then find out that after 35 years of putting $1,000 into the plan, not adding anything else to it but this compounding interest, you will have $15,000, $996.50. And now you can see the power of compounding interest, that when you start with $1,000 and you end up with almost $16,000 after 35 years. All right, here's the second example that I'm going to have you actually finish on your own. Determine the amount of an investment if $300, so there's our initial amount, is invested at an interest rate of 6.75%, compounded semi-annually. Okay, so semi-annually, annually means twice a year. So our n is going to be 2, And there is our time. So everything you need is right there in the problem. Be sure to change that 6.75%, move your decimal to the left 3 times, so that's 0.0675 for your R. Substitute those incorrectly, and let's just round it to the nearest dollar. And if you will, put your answer in. The correct answer is $1,132 if we round it. Okay, one final thought about compounding interest. We've talked about compounding semi-annually, twice a year. We could compound it quarterly, 4 times a year. We could do it monthly, 12 times a year. And so as you notice the denominator here, this is getting larger, right? For monthly, that would be 12. If we did daily, that would be 365. What if we did hourly? Or if we did it every minute, every second, every nanosecond of a year? This number is getting really, really large, and we're getting to the point of what if we just continuously, every nanosecond, this thing is growing. And that's going to be our discussion for tomorrow, is this continuous growth. So I hope you look forward to our lesson tomorrow in class. See you then.